Okay, so number 5, the engine of a spacecraft heading to the moon provides a thrust of 1,800 newtons. If the spacecraft has a mass of 600 kilograms, what is its acceleration? Yeah. In meters per second squared. Okay, so all we need to know is the F equals ma from physics, right? Force is equal mass times acceleration. We have the force in newtons. We have the mass in kilograms. The other thing is remembering what is a newton. Do you remember the units for newtons? Okay, let me find them for you. Doesn't work with that file, but
Is it 1 kilogram per meter per second?
yeah, that's it. 1 kilogram times meter per second squared. So they want the answer in meters per second squared, so we already have that piece here, right? So I'm gonna go ahead and write that. Force is 1,800 newtons, equal to the mass, 600 kilograms times A. They want to know A, basically. So what we want to show is that this 1,800 newtons is really 1 kilogram times meters per second squared. So I'm going to change the newtons to this just so you can see it. The answer is pretty obvious to find, but just so we practice with our unit stuff, we're going to divide both sides by 600. So we have 1,800 kilograms times meters per second squared divided by 600 kilograms. So the kilograms will cancel. And I'll divide both sides, right? So these are gone. So then A is equal to, what is that, 3? So that'll be your answer. So you'll type in on your test something 3 meters slash S, and then put the 2 as with a caret. Okay. Like right here, let me write it on the keyboard so you can see what I'm saying. The 3 meters per second squared. We would type it in something like that. Let me double check though. Yeah, so oops, I missed a zero. This is actually 18,000 up here. 18,000, which makes us 30. You would type it this way. 30 meters per second. There's a space in between meters and 30, and that's it. You guys have any questions on number 5? Okay, so number 6. How much does the spacecraft from problem 5 weigh on Earth versus the moon? Give your answer in newtons. Okay. So we have the mass of the spacecraft, right? So all you have to do is find the weight. Just remember that weight is technically a force. So F would be equal to the weight on Earth. That'll be the first one, which is going to be the 600 kilograms times the gravity of Earth. So we'll do 9.81 meters per second squared, which will give us about for Earth, that would be 5,886 newtons. Now for the force equal to the weight on the moon, you take the 600 and multiply by the moon's gravity. It should be given in the problem, so I'm going to go ahead and write it here. So that should be, let's see here. $960 newtons. And if you discover if you ask for the difference, right? They said, what does it weigh? Earth versus the moon, so they want the difference. So the difference is equal to 5,886 minus 960 newtons, which is equal to 4926 newtons. Do you have any question on number 6? Yeah, something like that on the test. Okay. Number 7. One second. 400 kilometers. We have time, 3 days. If we look at question 5, we also have the thrust of the spacecraft. We have F equal to 1800. 1800 or 18,000? 1,000. That makes more sense. We have the mass right, equal to 600 kilograms Okay. So let's look at the formulas that we're going to need. Just in case, I'll write the power formula. It'll be work over time. Work is equal to force times distance. One second, let's get the other guys. Delta distance, energy, just in case I need them all. Here they are. All right. So let's find work first. So we have a force of 1800 newtons, 18,000 newtons over some distance. So we'll most likely need to multiply this stuff here, then divide by time. We should be all right. Let's get back to that question. Okay. So mosquito biting me right now. So be okay. 1,000 times. One moment. In a day. So the number of seconds in a day is 86,400. So the amount of work done should be 1,800,000 newtons times the distance, which is going to be 384,400 kilometers. Okay, that'll give us a giant number. So then power should be this amount divided by time, which will be 3 days times the number of seconds. Okay. There we go. So power will be in units of, let's see here. That'll cancel kilometers squared. Yeah, that should be fine. The only issue is once you do this, you'd have to change to horsepower. That's the only thing missing. But I'll send you this guy later because I need to finish this thing. I'll come back to this. Okay. Here it is. Power. Yes. Okay. Yeah, so we can use, now I found the correct formula here. So power is equal to energy divided by time. Here we go. So I don't need the work necessarily, although it would have worked anyway. But to use the notes in our that we have in our PDFs, let's go ahead and use this guy. So this is actually E. There we go. Finally, sorry guys, we'll find that PDF. Okay, so the units would be in horsepower. So technically, power in SI units is watts. So we'd have to convert it to horsepower. So let's write down that. Let's go ahead and finish it now that I found it. Okay. Yeah, so this is going to be watts. Alrighty. Yes. So the conversion factor we're going to need is that 1 watt is equal to 0.00134 horsepower. Okay. So we need to know what is a watt. So a watt should be, let me double check. It's kilograms times meters squared per second squared. So let's double check. Here it is. So a watt is technically kilogram meters squared per second cubed. Yeah, that should be fine. We'll use that guy. Yeah, okay, so back to the question. So we have currently we have kilograms right here, because Newton is technically a kilogram times meter per second squared, so kilograms times the meters, which is right here, per second squared. So this will make it second cubed on the bottom. So yeah, this will be in watts. So this answer will be correct. Plugging all that nonsense in, be 18,000. 18,000 times 384, 400, divided by 3, divided by 86, 400, will be this. This will be 26694.4 watts of power. So that's the unit of the power the spaceship is outputting, but we want to go to horsepower, so we got to convert it. So 266. Sorry, I wrote that off. Messed up. Okay. So 266 269.4 watts multiplied by your conversion factor. That will be 0.00134 horsepower per 1 watt. So these watts are gone. So we'll multiply this original answer times 0.00134. So this is, let's see here, seems a little small. 2269 watts. Let me double check this horsepower. I think that's too small. Horsepower is 0.00134. Oh, right. This is fudge. Kilowatts. I forgot. Because if you look at the formula, right, they have it in meters. So I have to change. You have to first change this to meters, which will give you an extra 1,000 units. Okay, there we go. So this is actually K, kilowatts. Okay. Canceling the watts. So now we have, looking at our calculator, we have 35.77 kHp, which is not a unit, right? So I got to change that. That'd be 3,000. 35,000 horsepower. That makes more sense for a spaceship because 35 horsepower would be stupid. It doesn't make any sense. Now, oh, sorry. Mosquito keeps biting my feet. It's really distracting. So, the main thing you need to know is changing this, is finding the total energy. So when you do this guy right here, I should have changed it to meters. Okay. So this would have been 18,000 times 384, 400 times 1,000 with a K. It'd be a huge number. So this would be 6.9192 times 10 to the 12, I believe, joules. So then you divide this guy, or you could just say Newton meters. Kilograms times meters squared per second squared. Newtons is technically kilograms times meters. So I can multiply this meters times that meters, giving me the, man, the whole thing's weird, giving me 2. Anyway, is there any questions on this problem? I know I was a little, couldn't find that damn sheet for a bit, but I'm hoping I didn't throw you off too much.
Where are you finding the horsepower equivalent on what handout
That one,
is that on?
that handout is on, let me just go ahead and share it now. It's on the last homework page of homework 4. The one that has power, it's called power. So power, you need power and energy. Let me just change it to Newton meter. Power and energy PDS for this problem. Because they talk about work and they talk about these equations. This is actually a Newton meter, which is a joule. I'm going to share the screen with you right now.
For the exam, could we have these handouts that show the formulas?
Yeah, that's fine. You're allowed to have one page front and back, whatever you like. If you want to put them all the formulas on there, it's fine. Or because I don't know if Lockdown Browser will let you view them, so you might want to just write them down somewhere. Yeah, I think that's right. I think that'd be better, actually. You put all your formulas on one page, and just scan that in with your work when you're done. But here's the stuff that I was looking at. It took me 5 minutes to find or so. So this guy here, the energy equation. Joules is technically the unit for energy, the SI unit, which is just Newton times meter, which is the force times distance, right? That's where you get this. Work is the difference in distance. So like from point A to point B, you can calculate how much work over a certain space, certain distance. Now, we didn't use any of these so far, but so that was the energy, and here's the power. That way I use this guy here. So you just need to know, okay, what is a horsepower? Well, it's if you go to one, this much horsepower for 1 watt, and a watt is equal to kg meter squared per second cubed. Any other questions on this problem? Okay, keep going here. All right, find the work. Exerted if a 42 kilogram object is lifted to a height of 1.8 meters at an acceleration of 3.4 meters per second squared. Give your answer in joules. Okay. All right, so let's write down everything that we know, right? Exerted is so we have a mass of 42 kilograms. We have a height or distance of 1.8 meters. We have an acceleration of 3.4 meters per second squared. And remember that a joule we said was a Newton times meter, which is the same as kilogram meter per second squared times another meter, right? So that'll remind us if we're going astray. So they want to know the work. So work, we said, is equal to the force times the difference in distance. So the difference in distance would be a starting point of 0 all the way up to 1.8. So you'll just put 1.8 here. the force we're going to have to find, right? Mass times acceleration. So force is equal to m times a. So we just find that real quick. 42 times 3.4, which will give us newtons. 42 times 3.4 is 142.8 newtons. Okay. We have the force now. We have the distance, so we should be able to calculate it for joules. So the work will be 142.8 newtons times 1.8 meters. So multiply our original by 1.8. That should be 257.04 newtons times meter, which is a joule, right? I wrote that out weird. (257.04 Newton meter, which is 257.04 joules. There we go. Do you have any questions on this problem?
No, sir, we're good.
Okay. Keep on going. Oh, yeah, it's time for a couple more.
So whenever you use the work formula, it always results in joules.
Work will be in joules. Let me double check. That's a good question. Where the heck is my energy for work? Yeah, it should be in joules. The only reason I was so sure without checking was because since it was in newtons, then I knew that multiplying by a distance in meters would give me joules, because joules is this, right? So in this case, yeah, but if your force is not in newtons, then I would say no, it would not be in joules. It would be in like calories or BTUs or something. Depends. So yeah, just make sure. If it's in newtons, then yeah, it will. It would say yes. Always it will be joules. Okay. Ready? Number 10. So some of these problems are from the last lecture that we didn't get to go over, but I would like you to go over the energy and power video, and then use these examples to help you get ready for that homework 4 and exam 1. Find the potential energy of the object in problem 9. And I should have your homeworks graded soon. I'm a little behind on the homework grading. My goal is to have it all ready before your test 1. In problem 9, if it is above the surface of Mars, give your answer in joules. All right. Okay, so gravity of Mars is what we're going to need, right? So this should be given to you. Gravity of Mars is 3.711 meters per second squared. They want to know potential energy. So let's go back to that PDF. PE is equal to mass times gravity times the delta H. Excuse me. So delta H is the same as the delta distance. Just some in this case, since we're talking about being above the surface of Mars, then we're going to look at a height. Did they say a height in this question? Let's see. Question did not say. So in problem 9, they listed the object in 1.8 meters. So we're going to be using that height, but we're going to be changing the gravity. Okay. So the potential energy for Mars, right, on Mars would be, that's mass doesn't change, 42 kilograms, times the new gravity of Mars, 711 meters per second squared, times, okay, difference of height. So from the ground to above, that would be 1.8 meters. So this is kilograms times meter per second squared is joules times a meter. That, oh, sorry, kilogram times meters per second squared is newtons. Times your meter would give you joules. So this will be in joules. So 42 times 3.711 times 1.8 should be 280.552 joules. This is the point. Yeah, that's what they got. Okay, let's see if I have time for the last one. Like 3 minutes left here. We can stay a little late if you guys are cool with that. If the object from problem 9 and 10 is released and hits the Martian surface at a speed of 6.7 meters per second, what is its kinetic energy in joules? All right, so let's go find our kinetic energy formula from the energy PDF. Kinetic energy is equal to 1/2 meters times velocity squared. We have, mass, not meters. 1/2 times mass times velocity squared. Should be right. Yes, that's right. So our mass will be 42 kilograms, right? That's still the object they've been talking about. They gave us a velocity of 6.7. So the kinetic energy should be 1/2 times 42 kilograms times meters per second squared. So this right here, half of 42, that'll be what, 21 kilograms, right? Squaring that, I forgot the 6.7. Squaring this guy. Let's see what that is. 6.7 squared. That would be 44.89. But then you get meters squared per second squared. So this will become newtons times meter, right? This is 21 times 44.89 kilograms times meter per second squared times another meter. See how I can just rewrite this? Which is going to be, this is just newtons meter. So our answer will be this guy times 21, 942.69 joules. Okay. Do you have any questions on 10 or 11? So try to write down all the formulas you're going to need, but I highly recommend you look at those PDFs and the video. Okay.